Hello and welcome to the 85B Vibratory Feeder Tray project. Our project is sponsored by Erie's Magnetics, a leader in magnetic separation technology. We were given the task of redesigning the 85B feeder tray to reach an infinite machine life as the previous design failed within 24 hours when it was given a 30% increase in output.
On the current feeder tray design, failure occurred where the drive arms are welded to the mounting bracket. Taking a closer look, a crack initiated at a stress concentration at the end of the weld. We focused our efforts on a design to eliminate this area of high stress. Our group examined a number of different avenues to remedy the cracking weld, including changing the mounting bracket geometry, the overall size of the weld, and the bracket to tray connection. After some technical analysis, the concept we chose is called the side flange design, characteristic of the two side flanges that help reduce the stress concentration. We got this from our concept selection matrix, and it performed the best in the areas of stress reduction, added mass, and manufacturability and cost.
We went through many different analysis methods to ensure the final design met all specifications and Erie standards. Seeing that the failure point occurs at the welded connection of the bracket and the drive arms, the welds were a key point to examine for factors of safety. Using the shear and bending weld stress equations as a way of analysis, the factor of safety for the problematic weld joining the drive arm and the mounting bracket was increased. Another key tool in this investigation was ANSYS Workbench, which allowed us to examine the stress on the tray and on the welds. Taking a look at the final design, there are many points of improvement. As a whole, the magnitude of all stress values decreased. This includes the drive arm, the crossbar, and most importantly, the welds.
With these geometric changes, we need to ensure the vibrations of the system was properly maintained. The vibrations model we created, as seen here, is split into 4 masses. These 4 masses are the base mass, armature mass, bracket mass, and tray mass. One can see the addition or subtraction of the mass in the bracket is critical for the vibration of the whole system. Transmissibility plots were created to compare the tray's movement to the desired distance. A transmissibility plot is a visual representation of the vibrations model. Knowing the input force, we plug that value into our vibrations model, and the transmissibility plot gives us a ratio to calculate the tray displacement. Lastly, manufacturing considerations. From a manufacturing point of view, the hardest component to manufacture is the side flange plate due to the large thickness and the large radius on this component. However, most steel cutting methods are capable to form this side flange, whether it be plasma cutting or hand cutting with an oxyacetylene torch. As a whole, the side flange design is successful at achieving infinite life. The stress on all components has been reduced to satisfactory numbers and all specifications have been met. We would like to thank our faculty advisor, Professor Wu, and our sponsors at Erie's, Chris Sedzo and Jason Benser.